In this video, I'm going to introduce you to some new probability rules and some terminology. We've got a Venn diagram here and we're being asked what is the probability of picking someone at random who likes apples and pears. So to write that in notation, that will be P, A and P. So to do this, we need a fraction for a probability. So the bottom of our fraction will be the universal set. So we need to add up all of those numbers. So we've got 32, 28, that's 60, plus 10 is 70, plus 24 is 94, plus the 6 is 100, and 12 and 8 make 20. So altogether we've got 120 to go on the bottom. So for the top we need to work out what's in A and P. That's this area here, and we can see we've got a 6 and an 8, and if we add those together we get 14. And as with all fractions, you should simplify it. So this becomes 7 over 60. Same information but new question. So we want the probability of picking someone who doesn't like apples and doesn't like bananas and doesn't like pears. So we'd write that as the probability of A dash, B dash, C dash. Still going to be out of 120, but we need to work out what region we're interested in by drawing our diagram again. So we want to shade everything that's not A. Then everything that's not B in a different direction. And then finally, everything that's not P. Sorry, I put C in earlier. It should obviously have been P for pears. I'm going to use a wiggly line for the P. What we're looking for is the area that has all three different types of line in. Try and outline that for you. See, that means that we're talking about the area that's outside all of the circles. So that means that it's got 28 in it. So our probability equals 28 over 120, be 14 over 60, which is 7 over 30. This next one, we're being asked the probability of picking someone who likes either bananas or pears or both. So that's the probability of B union P. Have the same bottom, 120. Let's use this diagram to work out what region we are interested in. So we're going to need everything that's in bananas, which is 24 plus 12, which is 36, plus another 6, which is 42, plus the rest that's in pears, so that's another 8, which makes 50, and 10, which is 60. So we've got 60 out of 120, which is a half. If you weren't using a Venn diagram, you'd need to use this rule. So the probability of B union P is the probability of B plus the probability of P minus the probability of B and P. Why do we have to take that off? Because if we've done all of the bananas and added them up and all of the pears and added them up, then we will have duplicated that 6 part that was in the middle here, look. So we have to take that off if we're doing it numerically without a picture, so that we don't duplicate. I'm going to introduce you to something new here. So we're doing the probability of picking someone who likes apples, given that we know they like bananas. So we write that as the probability of A with this line B. That line means given that. This means that we're restricting ourselves only to what's inside of the bananas, the green circle. So in effect, our universal set is shrinking to just bananas. And so the bottom of our fraction this time will be the total number of bananas. So that's 24 plus 12, which is 36, plus 6, which is 42. Then on top, we need how many apples are inside the bananas. So that's 12 and 6, so that's 18 to go on top. Simplifying that, we get 9 over 21. Divide by 3 and we get 3 over 7. So let's have a look at the notation form in case you don't actually have a diagram for this. So the probability of A given B equals the probability of A and B divided by the probability of B. See that the 18 was what was in the overlap between the apples and the bananas. That's what went on top. And on the bottom we put how much was in bananas altogether, the probability of B. So let me introduce you to the term mutually exclusive. So this diagram demonstrates what Venn diagram would look like if the two sets were mutually exclusive. So you can see that there is no overlap. So there's no overlap because they can't happen at the same time, or both can't be true at the same time. So if two things are mutually exclusive, then the probability of A and B will be 0. There's no overlap. And the probability of A union B will just be the probability of A plus the probability of B. Remember the formula that we had before? We had the probability of A union B was the probability of A plus the probability of B minus the probability of A and B. But if that is 0, there's no point including that. So an example of something that might be mutually exclusive, if A was odd numbers and B was even numbers, then they can't happen at the same time. It's either an odd number or an even number. Independent means that event A doesn't change or affect the probability of the event B. So an example of something that would be independent would be if we were to roll a dice and then toss a coin. So if we were to get a 6 on the dice, that would have no impact on whether or not we got a head or a tail when we toss the coin. Just doesn't affect the probability. So let's look at the notation. So if something is independent, that means that the probability of A given the probability of B equals the probability of A, because the probability of A is not changed dependent on whether B has happened or not. Now you may be asked to prove that something is independent, so you could use that, but we also have another version based on that, and that is that the probability of A and B equals the probability of A times by the probability of B. So this comes from the other formula I just showed you, where we had that the probability of B given A equals the probability of A and B divided by the probability of A. I know I've written it the other way round, but if the probability of B given A is the same as probability of B, and we multiplied both sides by the probability of A, you could see how that would give you the new formula that I've shown you. So dependent, also called conditional, is the opposite of independent. So this means that the first event does affect what happens in the second event, or the probability of that happening. So here we have an example. We've got a bag of 12 buttons, 8 are red, 4 are blue, and we need to pick 2 at random without replacing the first one. The probability of us picking a red button first of all would be 8 out of 12, and for the blue it would be 4 out of 12. If we've already picked a red button out though, there will only now be 11 buttons in the bag and only 7 of them will be red, so the probability changes to 7/11. Probability of blue would change to 4 out of 11 because we've still got all 4. And then if we've taken a blue one out first of all, the probability of red, still 8 on top but 11 on the bottom, and the probability of picking a second blue one would only be 3 out of 11 because we've already taken one blue one out.